This is the Advanced Succession Award from 2019. Let's just go into it. We're supposed to prove this thing. Now, you can use change of base law. I didn't know that you could do that because I thought in a show that question you have to do it properly. Change of base law, by the way, is this. Log of AB is log of whatever base you want, in this case Taylor Swift, of B, divided by that same base, log of that same base, A. You're allowed to use that apparently. I didn't. I just raised both sides to the power 4. Then I said 4 is 2 squared. You could multiply the 2 and the u here. You could take log to base 2 of both sides now. You can cancel this 2 with this 2, of course, log to base 2 of 2 to the power. Or, of course, you can think of this as going out to the front and then cancel log to base 2 of 2, because it's just 1. And then, of course, we can just divide by 2, and u is that thing that I originally said here. And we've got our answer. So, yeah, I thought that was the proper way of doing it. Essentially, I'm just proving change of base law by doing it that way, but whatever. Now we have to solve this. Of course, we're going to use this to do it because we don't have a match of logs here. So let's replace this log 4 with this. So it's a half log base 2 of that same function there. We can bring this half up to the front, up to the top here. Now we can cancel these two logs, and now, of course, we can square both sides. We can do some very standard algebra stuff. We'll eventually get this. It all halves, it factorizes, and we end up with our two answers, I believe, of 3/2 and 6, which are both positive. So they both happily will go into a log. However, here we can see we're also taking away stuff. So let's just check both. If you put in 3/2, 3 times 3/2 minus 5 is, 3 times 3/2 is 4.5, I think. So minus 5 is less than 0. And so that's not a solution. X is 6 is the only solution. Just check that it works in here, but it does. And it definitely works in here as well. So X is 6 would be our solution. Very nice first question. Hope you all got 7 marks. Question number 2, got a binomial. I feel a bit ambushed here because I didn't do this paper to do stats. I don't do stats. I hate it. So I'm a bit annoyed that this is on this, but I guess looking back, it is on the spec. It does warn you that they might ask you some stats. So anyway, we have a binomial function, and the mode is m. That means, if you imagine, so a binomial is, you only have two outcomes, you have a number of trials, you have a probability. Just imagine it's flipping a coin, right? Probability of half, heads or tails. Just imagine you do it 100 times. The mode for that sort of trial experiment thing will be 50 heads, right? That's the most likely outcome, is you get half heads, half tails. It's a very unlikely outcome, incidentally, but it is more likely than 49 or 51 either way, right? And that's basically what this question is doing, right? We know how to work out a binomial if we've actually managed to stay awake during stats lessons. It's this. And then it says determine an interval of width m in which m lies. Well, we just have to do that thing where we say, okay, based on what I just said, the probability of m happening is just more than the probability of m minus 1, right? So the probability of 50 heads, because it's the mode, is more than 49, right? But of course we could just set up this same kind of idea with m minus 1 in here. So that's what we do with a less than or equal to sign in it, and we get this. Of course we could very carefully work through this. Lots of nice things cancel. The fact that we're actually doing proper maths now is nice. I can't remember what I did here. I cancel 1 minus b or to the power n minus b. I'm just left with one of them over here. And of course, p to the m divided by p to the m minus 1, you can just get a p over here. N choose m, you can write as this. So it's n factorial over m factorial, n minus m factorial. And then more stuff cancels, right? N factorials cancel. We can also cancel, we could write this like this first. But then m factorial cancels over here with that, just leave an m left over. You could do this much slower if you want to. Now this is just one more than that, so again, lots of cancelling here. Or, this is just that with an extra term at the top, so it's just going to become this, and all of that will cancel away. Of course, now we can just sort of cross multiply, and I think I'm eventually just kind of rearranging for m. The fact that some stuff cancels is very kind. It means the m is nice to rearrange for. Now that's the condition by which m is more likely than m minus 1. But of course we've also got to look at the other side, thinking about the heads tails example. This means 50 is more likely than 49 heads, but we also have to say it's more likely than 51. So and this is where I just literally copied and pasted an absolute ton of slides, or really just one slide with a ton of animations in it. Everything is exactly the same. Exactly the same cancelling happens, it just ends up being a slightly different thing at the end. You get this. So m has to be in between these two things, which is width 1, isn't it? Because, I put it here. Width 1 because this is just 1 less than that, which is cool. Find a value of n such that there are two modes. Well, look at this carefully. If this is width 1, right, this thing here is 1 less than that. Now that's fine if, like, this thing here was 1.5 and this was 2.5, because that would, you could say the mode was 2, right, which is a nice whole number, which is good. But if this was a whole number, then that would be a whole number, and m can't be sandwiched between two whole numbers and not be equal to one of the two, therefore making you have two modes. So we just require one of these two things to be a whole number or an integer. We could factorize out, we could just look for values that would make this integer, we could just choose a value of n and p that will do this. So I just found this where, because of course when you add 1 to that you get 200, times by 0.1 is just 20, and we can say m is either that 19, because I'm saying this is 20 here, so either m has to be 20 to join it, or you could make m 19 there and you'd have two modes of 19 and 20. So yeah, kind of, I thought it would be awful because it was stats, and it was awful deep down, but it was kind of not as awful as it could have been. Anyway, given phi is this thing, which hopefully you recognize as the Gaussian ratio, which is quite nice. Show this thing, so this is just some boring maths, right? We just square out, half squared is a quarter, square this, you just do some expanding out. If you want to, although, okay, so I did eventually cool. I thought I was going to do it in a more intelligent way in a second, but I didn't. You get this, you could sort of, obviously cancel the 2's there. You could write 3 as 1 plus 2, I believe. And then you could expand out this half into this thing to make a half into that, which is phi. And then you could expand the half into that just to make a plus 1, and you get phi plus 1. So that's cool. For the style mark, you could do this without any real computation, because you could just take this, divide by phi, and then you could just say, well, rearrange it, mate. So if you know this to be true, this is just true by this. So you could get away with no computation. Of course, you could just do 1 over this and do some rationalizing, and you eventually get to this in a similar sort of method that we did. But it's much nicer like that. Anyway, two curves have these two equations that we're supposed to be looking for. So this is what they told us first. We're supposed to be looking for the intersection point where they touch. They're tangent to each other. Now, if you just try and find the intersection by setting these two things equal, things go badly straight away, because I don't know of anything like an A-level method that's non-calculator that would get me that solution there. So we don't do that. The fact that they touch the fact that they touch a p is important, because what that means is their gradients are the same at the point they touch. So well, their gradient is dy by dx, right? So let's differentiate both of these. We get this. This is x minus 1, so it differentiates that. Log differentiates to 1 over x, so that's just minus 1, and that differentiates to 0. And these two gradients are equal at the point where they touch, so we can say this equals that. And that looks like a much easier thing for me to solve. Times everything by x squared, and rearrange. This is actually just this, right? Phi squared minus phi minus 1 equals 0. So the solution to this is just phi, so we know the solution is that, which is this. And then, of course, y we could just say is 1 over phi, which is phi minus 1. And so y is phi minus 1. So our coordinates are just phi, comma, phi minus 1. The value of k, well, I mean, we know the coordinates now. X is phi, y is phi minus 1. Just put those into there, and we'll find the value of k in terms of phi. And it's that. And we have question 3 done as well. So excellent, making good progress here. I'll go to question number 4, which is quite a complicated question about trig, although I thought it was quite nice. We'll look in the formula book for the trig equation about cos of compound angles. So that's that. We also need the side, what it looks like, so I'll bust that out as well, which I think is here. So the left-hand side is this. I'm just expanding out, I think. I've replaced cos x minus y with this. The minus turns into a plus, so it's that. Then I just expanded, because I couldn't think of anything else to do. And now I'm trying to get this back again, this sine compound. So we're looking at this, like, okay, well, clearly some factorizing is necessary. So, okay, well, there's cos x is here and cos x is over there. So let's just swap these two middle terms over. Actually, before I did that, I replaced the sine squared and the cos squared with 1 minus sine and cos of the other one, and then expanded everything out. And the reason I did that was because I knew it would give me sines of y and cos of x, which on their own, which I didn't have before, and I can see from here that I need, because when you expand it out, that's what you get. So okay, I've done that. Now I'm noticing that I've got cos x is here, cos x is here, sine y is here and here. So let's swap those two middle terms over. I'm happy with these two terms. Let's factorize out cos x from that. AEA is 3 hours long, by the way, so you have plenty of time to think through these methods. But finally, we look at this, sine cos, cos sine, sine cos, sine cos. that's just sine compound formula backwards, right? So I think I can say this is that, and this is that, just using this formula this way around. And this factorizes nicely, doesn't it? Because I planned this. 1 times this gives me that, 1 times this gives me that, and then this times this is that, and this times this is that. And so that is the right-hand side just there. Now part B is similar, it's more proof. Not obvious where to start here. Like, how do we, obviously we need to use this. How do we use this to even make a start here? Well, it's sine plus cos, and cos plus sine here. So why don't we take this and sort of cross-divide, put this over there and this over there. And what's that really helpful for is it gives me this, but if I set x to be 5 theta and y to be 3 theta, I think this left-hand side is this. But I also know this must be this, which is 1 plus 2 theta into cos 2 theta. So I think I end up with this. That seems good progress. So now I just need to show this is this. Well, I've got some formulas here I can use. Sine 2 theta is just 2 sine cos. We should know that. We should also know this one. You can write 1. This is generally a pretty useful trick to bear in mind when you're doing proofs of trig. 1 is cos squared plus sine squared. And so this entire top thing will factorize to be cos plus sine all squared, which is cool. It's also cool that, or quite cool maybe, that means actually you could memorize, if you wanted to, this result, that 1 plus sine 2 theta is just this. That might be a useful thing to have in the back of your mind if you ever see it. But anyway, so you have this, and then you can cancel this with this, and you end up with this, which looks like it could be getting towards this. We're not quite there. We also, by the way, of course, need to require that this is not equal to this, which means tan theta is not equal to -1. Now from here, how do we make any more progress here? Well, okay, what we can do is we can say sine theta, tan is sine over cos, so cos times tan is sine. And then, of course, we can factorize out the cos, and we can cancel them. Of course, again, we require cos theta not to be 0, and we'll have the right thing with these two conditions in place. Now, show this as a unique solution. Well, we just need this. Obviously, this equals this, so we need this to have a unique solution of k. And yeah, we can just multiply across. We can factorize out, or we can move over the tan to then factorize and get everything in terms of tan theta. Now, this thing here is greater than 1 because greater than 0 because k is greater than 1. But it's also less than 1 because the top is smaller than the bottom. And of course that means tan theta is locked, just like this is, between 0 and 1. But tan theta is just a very boring increasing function between the values of 0 and pi over 4, isn't it? So if tan theta is locked between those two things, that just means theta is between pi over 0 and pi over 4. And so therefore we have a unique solution, I guess. Cool. Question 5 then is on vectors. So we're going to draw this out, I guess. We've got points A and B, position vectors A and B respectively. So it looks a bit like this, I guess. Confusingly, we're told that the length is A and the length is B. So there's going to be some very careful bold A's for vectors and not bold A's for lengths to do here. But that's okay. And then we've got position vector C that bisects A and B, so this angle equal to this angle, and C is just somewhere along there with that angle equal to that one. Good. Prove this is perpendicular to C. Now, okay, let's actually set up these two vectors here then. So BA is just this vector A done B times. So I'll almost sort of zoom out of the picture a little bit and multiply this vector by B and make it now be the vector BA, which has length AB, because of course the length of A is just A. So if I have B of them, I'm just going to have length AB. And I'll do the same with point B over here. So I'll kind of extend B out by times by A, and we get this. And now the vector BA minus AB, well, that's going back through here. And then this one, isn't it, I think? Because it's this one minus this one, so it is this vector from there to there. So that's that vector, and we're showing that it's perpendicular here. Well, if these two lengths are both AB, then that means they're equal. So this is an isosceles triangle. But even more than that as well, and I actually don't know whether I need this, but this triangle and this triangle are congruent by SAS, because they share a side here, they have two equal sides here, and an equal angle here. So SAS congruent, which means if that angle was like alpha, so is this one, because they're congruent. But of course, from here I can say, well, again, looking at this triangle, 2 theta plus 2 alpha is 180, or pi. Divide everything by 2, and you get theta plus alpha is pi over 2, which means the remaining angle in each of the triangles must be pi over 2, which is of course a right angle, which makes them perpendicular. So I think I've shown that for the 4 marks. The next bit, D, is on AB. So we'll go back to our original picture, so we won't scale it up anymore. We'll go back to the original picture, which was this. D is somewhere on AB, and the vectors from there to there is D. Show this thing here. Well, okay, to get from the origin to D here, I could go up to A and then down here. Now this vector from A to B is just B minus A, of course, because it's just minus A plus B. So A to D here is just some amount, which we could call lambda, in between 0 and 1, because we're still going in this direction, but we're just not doing the entire thing, so it must be less than 1, and we're going in this direction, so it must be more than 0. So with lambda between 0 and 1, I can say A to D is just lambda of B minus A, which means O to D, which is D, is A plus that thing there. What I just said. And now, of course, we can just factorize for A's, and we'll get the thing they wanted us to get. Now, C, I have no idea how to do without dot products. There is a mark scheme explanation that's being attempted to be made, but I didn't understand it. So apologies for the fact that I'm about to use a dot product, which I know is only a further maths thing, and this paper is supposed to be available to, or doable without any further maths, but I'm just going to use a dot product because it's the only thing that I could really understand how to do. So D is also on OC, so we're immediately tricked that this thing might be kind of relevant, because we now know that D is perpendicular to this, and that's what I was thinking. Dot product says two perpendicular things have a dot product of 0. So what I said here was that, well, I've already expressed D as this. If I dot that with this, I should get 0. Now, this gets a little bit complicated here because, I mean, firstly, the dot product, you can just expand out from it. So that's fine. So we'll just do this dot this minus this dot this. So that's fine. Now, A dot A, any vector dotted with itself, is just the magnitude squared. So A dot A is just this A squared, the length of it squared. So and of course these numbers don't, these are just scalar numbers, aren't they? So this first bit here will just be B times 1 minus lambda times A squared. Now the second bit will of course just be B times lambda, and then I don't know what A dot B is, so I'll just write A dot B here. And likewise for the rest of it. So the only thing that happens here is B dot B is also just B squared. Now here, what I did was I just expanded everything out again, or kept going with this. We got this. I then decided to group everything by lambda, of course, because we're trying to solve for lambda. So let's just group all the lambdas to one side and get rid of all the non-lambdas over here. Now this is a hard spot right now, but clearly I can factorize an A from this side to get A brackets A dot B minus AB. And what I was thinking over here was, well, hopefully I can do that as well, because this sort of looks like it might factorize into something like A and B with this thing somewhere, and it does. If you stare hard enough, you should be able to find this. A times this is that, B times this is that, A times this is that, B times this is that. Right, so that's fine. And now, of course, if I could just cancel these two things, that would be great, because I get lambda is equal to A over A plus B. Let's just justify that I can just cancel these things, and we just need to know that the dot product is defined to be this. It's the two lengths multiplied cos times by the angle between them, which I'm sort of saying is 2 theta here in this case, but let's ignore the picture because we don't need it anymore. It's just this, with alpha being the angle between them. But that of course means that if A dot B minus AB was 0, that means A dot B equals AB. Now here, if A dot B equals AB, that means cos alpha needs to be 1. And that just happens when when alpha is 0, or 2 pi, or 4 pi. Basically when you're in the same place, right? And we know our A and B aren't, and so we know this isn't the case. So we're happy to we know that this thing isn't 0. So we're happy to cancel those out, and we'll get with this, and then we'll have to divide them when we get this. That's good. So we'll have lambda is equal to that in terms of A and B, and then hence show this. Now here, OA is just A, and OB is just B. There's no vector things over this, so this is the lengths. So that's just A dot B. Cool. Now dA, now the vector D to A is minus D plus A. Now we know D is this with lambda being this, so I can put that in if I want to. I will eventually. Notice that they just cancel, and then you can factorize out the lambda, and you get this. Now dB, same thing, it's just minus d plus b, which is this, which is this, which is this. Factorize out the lambda minus 1. Now 1 is a plus b over a plus b, so this is a minus a plus b, so that's just b over this, and we get that. Now the length dA is just, well, this times the length of a minus b, and the length of dB is that times the length of a minus b. The length of a minus b is non-zero because they're not in the same place again, so I can cancel those out and we'll just get this times by a plus b, and we'll just get this, which is the same as that. And so we have what we're aiming for. Right, a really nice question about calculus here. We've got this curve here between 1 and a, find the coordinates of a. So the curve is just that, so we'll set that to be equal to 0. We'll obviously have that either x is 0, which is irrelevant because x needs to be bigger than 1, or we'll have sine of log of x equals 0. We could inverse sine here, and we'll get either 0 or pi. Of course, you'll also have 2 pi and so on, but I can sort of tell here that, of course, if I raise both sides, or do e to both sides, I'll get x is e to the 0, or e to the pi, or e to the 2 pi, but I don't care about the next solution after this one. The first one is e to the 0, which is 1. Second one is e to the pi, and we'll have our coordinates of e to the pi is 0. There will be another one over here and another one there, but it doesn't matter. Good. Differentiate this and this, so this is going to be lots of product rule. Differentiate the x just for a 1 to get this, leave this one alone. Differentiate this after having left that one alone. This differentiates to a cos straight away with a log of x, and then you differentiate the inside of the function, so that's just going to be differential of log is 1 over x, and that actually cancels and you just end up with this, which is nice. Same kind of thing happens here, except the only difference is there's a minus sign here because cos differentiates to minus sign, and you end up with this. Good. Hence find these two things. Kind of interesting here. What we can say is, well, if that differentiates to that, that means that the integral of this is that. I've not done any plus c's for any of this question because I sort of know that AEA don't care about them for some reason, so I couldn't be bothered to type any of them. So okay, that's just getting that out of the way. So okay, we have this. This result also tells us the same kind of thing, but first we can split this into two integrals to get this. And then of course this result tells us a very similar thing. This integrated is that, split up into two integrals. And what I can do here is I can now say, okay, if I add this result here, this one here, to this one here, integral of cos plus integral of cos is 2 integrals of cos. These two things cancel, and so I have 2 integral of cos of log of x equals to this plus this, divide by 2, and we get that one. And I can find the sine one just by doing this minus this. Right, this minus this is 2 sines, because minus minus is plus, so 2 sine log integral of. These cancel, so it equals this minus this, and then you just divide by 2, and you end up with that result there. Hence find, oh sorry, that's what we did. Find the integral of x sine of log of x. There's a few ways of doing this, but what I decided to do was parts. Because if I integrate this one to an x squared over 2, and then of course leave this one alone, take away the integral of, again, still integrate this one, but now differentiate this, which I know the differential of because I've actually already done it. It's just cos of this times 1 over x. The 1 over x cancels with that, and I end up with an integral that's no more complicated than what I started with. Now it's a bit different, but that's okay. I think I can sort that out, because what I can do now is I can sort of do the same thing for the integral of x cos log of x. Exactly the same kind of idea. Cancel these two things out and we get this. And now what I'm going to say is that let's just let a equal this integral here and b equal this integral here. And I think I can write these integrals now in terms of each other, because I have that the integral of b, or just b for instance, this is the integral of this is b, so b equals this nonsense plus a half of a, and a equals this stuff minus half of b. And I think I could just rearrange these for, well, I'm looking for this one, which is a, right? So if I just shove this expression for b into there, which is what I've just done there, I can expand out. I can add a quarter a to both sides. I can times by 4, divide by 5, and I'll end up with an expression for a, which is the integral of x sine log of x. I don't need b because it didn't actually ask me to get that. Hence show that the area of the shaded region R is this. So I literally just need to integrate this thing here, which I know how to do, it's this, and evaluate between e to the pi and 1. That's all I need to do here. I've actually even forgotten to animate these slides, which I guess is okay because it's not that complicated, is it? I'm being asked to do this. We put in e to the pi, we put in 1 into this. When you put in e to the pi squared is just e to the 2 pi. And then when you put in 1, log of 1 is 0. And I should have mentioned log of e to the pi is just pi, so that's where those came from. Log of 1 is 0, and so we get sine of 0, cos of 0. Now, sine of 0 is just immediately goes away, so we end up with, and cos of 0 is 1, so it's minus a fifth, which is plus a fifth. This minus this is just one lot of that, and we can factorize it to the fifth, and we get this, and that's our final answer. Good. Question number 7 is the last question. It's a long one. I think it was, what, 20-something marks? But it should be worth mentioning that some of it was very straightforward. First bit then, we're going to need an expression for t if we're going to differentiate it. So, well, we start with just speed equals distance over time, right? Which means time is distance over speed. Distance here is x, and we're told that he goes at lambda meters per second along the edge of the thing. So the time it takes him to do this is going to be x over lambda. So that's our first bit of the time. So he's going to do this, then he's going to run along this edge to get to b. So we need to know the distance of this edge, which is going to be, well, this here is x minus a. Sorry, it's a minus x, of course, which means this length here is the square root of b squared plus this squared. And so that's the distance of this. Again, distance over speed. The speed that he runs through the marsh is just 1. So the time it's going to take him to do this bit is just this over 1, which is just that. So the total time is going to be this first time plus the second time, and we'll get that, which we can then, of course, differentiate. That differentiates is 1 over lambda. This is all to the power half, isn't it? So when I differentiate that, I'm going to bring the half down, which is here, going to lower it down to a minus half, and then derive by the inside, or times by the derivative of the inside of this. Now the derivative of this is 2 lots of a minus x to the power 1, with a minus 1, because the derivative of that is minus 1. So a few kind of derivatives inside derivatives to do that, but that's okay. Of course, now this times this cancels to get a minus in front here, and I think we just end up with this thing here if we rewrite that as 1 over this thing to the square root, and we'll have that fine. Good, so that's what they want us to get, so that's 5 marks that were not, I don't think, very hard. Find in terms of this for when that happens, so we just set that to be equal to 0. We can also do a bit of rearranging here. We can square both sides if we want to. I think that was probably my next step, so I just squared to get rid of this square root. Cross multiply. We could move this over and just factorize it out to get this, I think. And then, of course, we could just divide by this. We can square root both sides. We could move the x over and move this over to get this. This is just upside down because the plus would become the minus when you put it over there, and the minus would become the plus, and we get this. And just for the final mark, I'm just going to say the initial condition was that x is less than a, because of course you're not going to run past this point and then go back again, are you? So x is less than a, which means I don't want a plus this thing, do I? I want a minus this thing. So this will be my final answer there. Good. So we haven't done anything too hard yet in this question. Show that this value x lies in the interval this provided this. Now we already have shown that x is less than a. That's fine because we got this answer here. So now x greater than or equal to 0. Well, we just need this to be greater than or equal to 0. So we'll just make that greater than or equal to 0. We'll rearrange. We'll square both sides, I guess. We'll times across there, we'll divide by a squared. I'm allowed to do that because this thing is greater than 0, because lambda is greater than 1, which makes that greater than 0, so when I times by that, don't change that sign. Divide by a squared, plus 1, and I'll get this condition, which is, I think, when I square root, of course. When I square root, I get this, which is what they wanted me to get. For lambda in this range, show that the value of x gives a minimum. So again, we're looking at minimum values here, so what we're going to need to do, we have this value of x, we have this value of lambda. We're going to derive this again because, of course, we need to consider dt squared by d2t by dx squared is what I was trying to say there. This is not that easy to do. I've written it nice and small. You derive this for just a minus 1, which cancels with that minus 1 and goes away. You leave this alone. This, of course, differentiates nothing. So I'm just doing product rule now on this. So derive that one and leave that one alone. And then leave this one alone and derive this one. Bring the minus half down to the front, that becomes a minus 3 over 2, times by the derivative of the inside of this, which is, again is 2 into a minus x to the power 1 times minus 1. So we get this, I think. This all tidies up to this. And yeah, we're asking, so for a minimum value, we want this thing to be greater than 0, right? But the thing is, when you write this out like this, maybe, to try and combine the terms together, so this is to the power 1 minus 1.5 is minus half. So I can do this. I can put these fractions together now because the denominators are the same. But of course, this minus this just goes away, so we just get b squared. But this is always greater than 0, because that's just greater than 0, and so is this. So, a bit of a misleading question, I thought, because you didn't use this value of x. It's kind of irrelevant, unless I'm missing something. It's just bigger than 0 anyway, so yeah, kind of weird. Anyway, question number C, find the minimum time taken. So we need to go back to our formula for time. Now, we know if lambda is greater than this, then we need to use the x value we found here. So we're just going to take this x value and put it into there. Of course, when we do that, I think we did this before as well when we put the x value. No, we didn't, sorry. When we put the x value into here, you get a minus this, which actually should really be a plus this, because this should be a plus. It absolutely doesn't matter, because when you square it, it goes away anyway. But so whatever. But it should be a minus brackets this to make this a plus. Doesn't matter. So yeah, this just squares out to be this thing on its own. Now I've written this. I've split this out into two pieces. I've written this as just this over this to make things come together to make this, and then factorize out the b squared. And the reason I've done all that is because, of course, this just 1 and minus 1 go away. And then I can root b squared lambda squared to just be b lambda. And I'll get this. And now what I think I can do, I did the similar sort of thing here, didn't I? I split this out and then rooted b squared for just b, and rooted this for this, and the root of this. Anyway, here I'm going to put all this together by timesing this one by the root, this one by nothing, and this one by lambda over lambda. So you get this, put all the numerators together, and you can notice that you get minus b plus b lambda squared, which you can factorize out a b from to get this. And now, of course, this is just this to the power 1, this is this to the power half, this to the power half. You can cancel this with half of that, and you get this. Now, actually, to get the 4 marks, I think this part was worth 3 marks, you had to get here, which I think was a little bit... I don't think that was great question design, because it doesn't really say you have to come up with any specifically simple solution to this. I think this should be worth 4 marks, or even this, just because it doesn't say that you need to simplify it. However, simplifying it does help you out with the last bit of this question quite a lot. Now, if lambda is between these two things instead, what this is saying is, now remember why we designated lambda to be bigger than this in the first place? It was in order to get x to be greater than 0. So if lambda is actually less than this, what we're saying is we don't actually want to run along x at all. We want x to be 0. So essentially lambda is now so small that it's not worth running along the edge. The speed that you run along the edge compared to the running through the middle is so slow that it's not worth running along the edge at all. You may as well just run straight through the middle, right? If lambda is between these two things. So, well, that's just root a squared plus b squared. You know you go through the middle at speed 1, so the time is just going to be this divided by 1, which is just that. So that's going to be part 2. And the last part, someone else runs at speed of lambda, but he doesn't like going through the marsh at all. This person just runs log here to here. So great, his total distance is a plus b, and his speed is lambda, so his time is going to be a plus b over lambda, time for Frankie. And we know that the time, given we're in this scenario, which is this one here, we know x needs to be, we know the time taken is what we just found before. It's this time that's taken here, if we're in this case. So we know that's the time for Edgar, and we just want Frankie to be, his time to be less than Edgar's, so we want this to be less than this. The lambdas will of course cancel immediately. The a's will cancel immediately, the b's will cancel immediately because they're positive. I'm allowed to do that. We can square both sides, we can add 1, and we can square root, and we don't need to worry about the negative solutions at all. We'll just get lambda is greater than root 2 as our answer. Thank you for watching, and I'll see you next time.